Thank you for having me. Today I'm going to tell you about moving fast, breaking things, and putting them back together. And this might be like a very different vibe to other talks in this science and engineering forum, because I'm not an engineer. I work in computer graphics. So our goal isn't to get things right, is to get them looking right. So like the measure for success is completely different in the work that I'm going to tell you about today. So I'm going to start with talking about this paper, which is a joint work with Jack Long, Leticia Matos da Silva, Aravind Ramakrishnan, Yushun Yang, and my advisor, Alec Jacobson. And I should make it clear that some of the slides that I'm going to use in the first half of the talk are by Aravind Ramakrishnan, who is my co-author and also works in our lab. So the problem that we're going to tackle is simulating how an object breaks when it receives an impact. And because this is a very relevant thing in fields like animation and computer graphics, for video games, for movies, you remember probably scenes of like a car exploding, things like that. This is a very important problem. So it's been studied a lot in the computer graphics literature. And there's a lot of these methods that might be more familiar to you as mechanical engineers, for example, that basically model the different forces that are inside the shape in some way and take very, very tiny steps in time to figure out how a crack propagates and figure out all the forces and basically do like all the force modeling of an object. However, that's too computationally expensive to work in real-time applications. So if you're doing a video game and you suddenly shoot at a window, there's not enough time to simulate all the forces propagating through the window and the cracks in the window appearing slowly. There's no time to simulate all of that. So today we're going to concern ourselves with the setup of real-time fracture simulation. So how do we get it good enough that it looks good for something like a video game? And in practice, most of the time, real-time fracture algorithms work in two steps. So first, there's a design stage where they pre-compute or they author or design a fracture pattern. So when you're designing the video game and you're designing this shape and you decide to add this shape to the scene, at that stage, you already author how it's going to break apart, right? So this is pre-computed before the video game runs. And then on runtime, when an impact is detected, the fracture event is triggered and the object breaks into all those pre-computed patterns. So this is how usually people get away with simulating fracture with very, very little time. You usually have like 1 or 2 milliseconds. So effectively what they do is they pre-compute the fracture pattern and then activate it when they detect an impact. And many of methods like these that are called prefracture algorithms have been suggested in the computer graphics literature too. However, we identify 3 key issues with existing prefracture methods. First, many require manual intervention. So many of these require someone to manually decide how the shape is going to break so that they activate them later. The ones that are fully automated produce very unrealistic fragments. So this is usually because they're based on procedural geometric decompositions that generate only convex pieces, and they're not taking into account what the shape's most clear structural weaknesses are. So they can be very, very unrealistic. And finally, all existing prefracture methods require some heuristic to decide which pieces of the object break off when an impact is detected. So even if you've already like pre-broken it into 100 pieces, when something hits it, you still have to decide which ones of those 100 pieces are actually separating and which ones aren't. And that's usually done with some heuristic that has no physical meaning. In the extreme case, this means that when an object breaks, it usually breaks on the same pieces regardless of what the fracture was. So if you've played Zelda, for example, The Legend of Zelda, and you throw a pod, the pod breaks in the same 4 pieces, regardless if you blew up the pod, if you threw it against the wall, if you hit it with a sword, it's pre-computed. So this is another key issue with existing methods. So today we're going to present an algorithm that's fully automated that's physically realistic. So it'll identify the geometric weaknesses of each object as potential fracture faults. And our framework will naturally lead itself to impact-dependent fractures at minimal runtime costs. So if you look at this video where the armadillo fell on its feet, it breaks its feet. When it falls on its face, it sort of shatters. And when it falls on its back, the tail breaks, which is what you would expect. It doesn't break into 100 pieces regardless. Our method is predicated on the well-studied field of modal analysis, which characterizes the most natural responses of a system. From modal analysis, there are three key properties that are fundamental to our method. The modes form an orthonormal basis, which means that any state, any deformation state, can be decomposed into a linear combination of modes. Orthogonal, meaning that energy cannot be transferred between modes, so they form a completely diverse and separated set of deformations. Modes are based on physical characteristic of a system, so this isn't just a procedural geometric algorithm, it's based on the physics of the system. And finally, each mode is an eigenstate of a linear system. So each mode has a corresponding eigenvalue, which is related to the energy of the mode. And computing things like vibration modes, or the most natural ways of deforming of an object, is something that's done very often in the literature, both for computer graphics and things like shape analysis or resistance analysis. So the elastic modes are an orthogonal basis that describe the most natural ways that an object has of deforming. And in our paper, we introduced fracture modes, an orthogonal basis that describe the most natural ways that an object has of breaking. So this is roughly the idea. We take something known as modal analysis that's very well used in our field, and we use it for the specific case of fracture. The modes are dependent of the physical characteristics of the system, including the geometry. We represent the geometry of an object using a triangle mesh in 2D and a tetrahedral mesh in 3D. And importantly, we restrict the object to only fracture along the mesh elements. The eigenvalue problem can be seen as an energy minimization problem. And you can check out the details of all of this in the paper. But basically, we minimize some energy subject to orthogonality constraints. And in the traditional elastic modes formulation, this will be the strain energy that we minimize. In this equation, we show the optimization problem where U is the modes and E psi is the strain energy. Extending this, we allow the modes to cause fractures, but we're going to add a discontinuity term to the energy that penalizes breaking the object. So we want it to break, but we don't want it to shatter everywhere. If you've done finite elements, this discontinuity energy is basically a cohesive surface energy from mechanical engineering. Since the discontinuity energy is a cost for breaking the object, it follows that more breaking should require a higher cost. In the case of two adjacent elements, it's easy to visualize this cost using a vector that represents how separated they are. But a real mesh will likely break in many places, not just along two elements, as in this simple example. So we need to aggregate these discontinuities somehow over all possible fractures. A natural first attempt is to use an L2 norm. However, it's well known that L2s in optimization will basically spread the energy over the entire solution. So here we see if we use an L2 norm, the first mode will just separate every triangle a little bit. And we definitely do not want that. It feels like the first mode should just break this shape horizontally through the middle. So let's keep trying. What about an L1 norm? It's pretty well known that an L1 norm promotes sparsity in optimization. So let's look at what that mode would look like. Something like this. This seems pretty reasonable, but there's still a problem. And the L1 norm of a vector isn't rotationally invariant. So the L1, if I rotate it, will be bigger than the L1 if it's not rotated. Well, it's kind of weird to think that an object will fracture differently if I just rotate it. Geometrically, physically, it's still the same object. So we would like this to be independent of rotation. Luckily, there's a solution, the L2-1 norm, which is a kind of a combination of the L2 and L1 norms. And we find that it induces sparsity like the L1 norm, but it also has rotational symmetry. Now we're ready to actually calculate the modes, but let's first make one model assumption. So we're going to target applications in video games that primarily use rigid body simulators. We can simplify the problem by only considering stiff, brittle fracture. So we will not assume that the objects exhibit any deformation before breaking. So they're rigid and then they break. That's it. So by construction, the strain energy goes to 0. So we can forget about the strain of the object because it'll only ever be either together or separated. It will not deform. And we'll enforce this geometrically by only allowing each mesh element to move rigidly. To solve the optimization problem, we adapt this algorithm, the iterated convexification for convex modes by Brandt and Hildebrand. They use it to compute vibration modes, but we're going to borrow it, make a small modification so that it's suitable to our fracture modes. The important part is that it's sequential. We calculate each mode one at a time, each mode is computed by iterating on a standard conic problem, for which there are many fast commercial solvers. We use Mosaic. Remember how the modes form a basis that spans the space of how the shape can break apart? Well, now it's time to use that property to turn an impact into an actual fracture pattern. This will be the only runtime step of the method. So once we detect an impact, we project it onto the shape and we see which modes get activated. This is basically the same way that you would project an impact into a drum to find which oscillations of the drum are activated. We basically do the same. If something hits the object, we project it onto the fracture modes and find which ones get activated to get the final fracture pattern. Now, the problem is that these shapes have to be very, very coarse so that we can use them, so that we can compute these fracture modes. But in practice, this happens a lot in video games. What we're going to do is we're going to use fine versions of the object, so a very high quality mesh that's usually called in a video game the render mesh. That this is the one that the user is only going to see. But in our case, we're going to create a cage mesh that completely envelops that mesh that the user will never see. We compute the modes on that cage, but then we transfer them to the fine mesh. Still, everything's happening in the design stage. Nothing is happening on runtime. On runtime, when an impact is detected, we do the projection step on the coarse mesh, and then we transfer that to the fine mesh, which finally gives us a broken object in real time. So we said that we had 3 success metrics that we set out for our method. The first one, is it fully automated? Well, for any object I showed you, we can compute its fracture modes. They look like this, and that's completely automated. So we get that. We don't need any manual intervention. What about physical realism? Earlier, we saw this example of a shape with an obvious structural pattern, and previously existing fracture methods didn't work. Our fracture modes perfectly identify this weakness. But even so, that's maybe a little bit too easy a test. So we do further tests just to see how realistic our fracture modes are. Fortunately, there's this algorithm in computer graphics by Joe et al. That already proposed a way of quantifying the weaknesses of different parts of an object. And they even did real world experiments, which for computer graphics is a very surprising thing, that you actually go and break things and see what they look like. So we actually reached out to the authors of this paper, and we got their exact inputs, and we ran our algorithm through those inputs, and we actually see that the places at which they break are very similar to the structurally weak places in their output and replicating the real world experiments. So I think we've gained the right, or at least in computer graphics, this is enough to say that your algorithm is physically realistic. Now, what about impact-dependent fractures? Well, for any shape, once we've computed the modes at the design stage, we can project any impact onto the modes and get impact-dependent fractures on real time. So for example, in the context of a video game, all you need to have is everything pre-computed, and then in real time, you can compute the different fracture pattern dependent on the impact. And this is done at minimal runtime costs. So we made this interactive application where you can generate random impacts and see just very quickly the simulated fracture pattern. And you can test out this app if you go to bit.ly/fracture modes, and you can play with it yourself and see just how realistic our algorithm is and how fast. So we've succeeded at generating impact-dependent fractures, which means that our algorithm is successful on all the 3 metrics that we wanted. Now, as we introduce our fracture modes to the community and beyond, we're excited about the kind of works that it can inspire. So for example, something we've briefly experimented with is author control. So in this example, where you have a light bulb, when a light bulb explodes, obviously the part that explodes is the glass part. It's not the rest of it. It's not the cable that holds the light bulb. So we can pass simple instructions like, this material doesn't break easily, this material does break easily, and then our fracture modes will respect that and it'll only break while keeping the hard parts together. Similar experiments show you that you can do the same to choose preferential fracture directions. So, for this object, we can tell it, this naturally breaks more in a vertical direction than in a horizontal one, and our fracture modes will respect that. Now, this was a very fun project to work on, mostly because breaking things and seeing things break is a pretty fun thing to do. But there's a very satisfying feeling to also to seeing things come together, right? And this is a project that's exactly about that, putting things together. So for this latest project, we teamed up with students Yunxun Chen and Ziyu Wu from the robotics department and their advisor, Professor Animesh Garg. And we looked at how we can use our fracture modes to put things together. So the task is now fracture reassembly. So something has broken and we need to design an algorithm that takes the pieces and tells you how to put them together so that you get the initial object. And this has many applications in artifact preservation, in heritage archiving, computer vision, robotics, which is the one that they were interested in. It's a practical thing, but it's extremely challenging and something it wasn't very intuitive to me because I thought, surely there are many algorithms that do very complex things in the real world. It can't be that it's that hard to find how two things fit, because if I just see two things, intuitively, I'm pretty good at that. And I feel like usually if a person can be very good at something, there's probably a machine learning algorithm that can also do it pretty good. But turns out this is pretty hard to do. And most solutions employ machine learning in one way or another to try and figure out, given two input shapes, how to put them together. Machine learning approaches require large-scale data sets of fractured objects. And this is their main limitation. They need to see thousands, tens of thousands, even millions of fractured objects to learn how to put them together. You not only need a million fractured objects, but you also need the instructions of how you would put those together so they can learn from their errors too. So there's existing data sets like PartNet, Automate, and Joinable that are supposed to work for this. The problem is that these are semantic segmentation data sets. They're not exactly the same as fracture data set. The difference is that an object usually has different parts. And these data sets are semantic in the sense that they separate the object into what intuitively a human would recognize are the different parts of the object. But when an object breaks, it doesn't break along semantically defined objects, semantically defined parts. When it breaks into geometrically plausible fragments. And these are completely different. So I think as things stand right now, they're using very suboptimal algorithms to train reassembly machine learning works. So this is the problem that Yunxun, Zi, and Animesh had for developing this type of algorithm. They just didn't have a large-scale data set of realistic fracture. So they reached out to us and they said, wait, didn't you just publish a paper on how to simulate fractures very fast? And this was super surprising to us because we had designed a paper, but our thinking was you may need to simulate fractures very fast because you may be designing a video game where you only have 1 millisecond to figure out how an object breaks. But turns out that another reason why you would want to simulate fractures fast is because you want to simulate a million of them in a day or in 2 days, right? And with previous works, you might have to take a year to simulate 1 million fractures. So this was a very eye-opening experience where we realized that doing something fast not only means that you can do it one time fast, it also means that you can do it at a completely different scale. So we introduced our algorithm, which we call Breaking Bad, a data set for fracture reassembly. And generating it is easy. We just select 10,000 possible shapes. These are not fractured shapes, these normal shapes that we find on the internet. And for each of them, we compute 20 of its fracture modes using our previous algorithm, and we get different breaking patterns for each object. And we repeat this until we get 80 different fractures for each object, meaning that in the end, we have 100 different fractures of an object, or 100 different ways in which an object can break. And that's 10,000 objects times 100 fractures per object. That gives us 1 million fractures, which is a massive data set of a scale that has never been considered in fracture reassembly before. We separate the data set into different categories in case you want to do task-specific learning. And finally, we test existing reassembly algorithms on our data set, which perform really, really badly. This is probably because they're thought of with this semantic understanding in mind. So we hope that releasing our data set, we've helped expose a gap in how these algorithms work, and we can serve as a tool for benchmarking and training future work in this direction. So if you want to know more about these works, you can find full papers and my code on my website here. And I'd like to end by thanking all the co-authors that literally made this work possible. And thank you for listening to this talk.